Hello, and welcome to the next video in my series on operations management. Now, just a reminder, these videos are for individuals that are relatively new to operations management. So if you are working on your MBA somewhere, these videos are probably a bit below what you would need. However, if you are just looking to understand the basics of operations management, maybe supplement your schoolwork or to help you with your business, then these videos are for you. So that being said, let's go ahead and dive right in. Now in this video, we're going to do something a little bit different, a little bit fun. Now, in my several videos before this one, I have talked about time series forecasting, where we use past data to try and forecast or predict future data. And the analogy I used in the previous video was this is like the weather person on TV saying the high tomorrow will be 85 degrees, but it ends up being 91 degrees. And of course, that's a 6-degree difference between the forecast and the actual high. And that 6 degrees we call forecast error. In this example, we're going to use some sports data. And actually, we're going to use the scoring data from the Miami Heat NBA basketball team. And we're going to figure out which forecasting model works best with the team's scoring history. So here's our problem. The 2012 NBA champion Miami Heat was by all measures a fantastic basketball team. Now the team manager would like to develop a scoring forecast model for next season, which is the 2012-2013 season. To do that, we're going to use data from the most recent season, which was the 2011-2012 season. So the question is, how can we implement forecast error techniques to determine which forecast model, the naive, the SMA, the WMA, or the EMA, which gives us the most reliable forecast data. So basically what we're going to do is we're going to look at last year's game data, the scoring data for the Miami Heat, and try to predict how many points they're going to score in the next game. So that's kind of fun. It's kind of cool, right? So let's go ahead and get started. Now I got the data from ESPN. They have the data for pretty much every sports team on Earth, or at least here in the United States, so you can go back and find how many points each team scored, their record, and everything else. So I did not have to search very hard for this data. You can find it on your own. Now here is the scoring graph for the Miami Heat for last season. Now I just want to point out that this graph actually begins with the 11th game of the season. And the reason for that is that in this model, we're going to be using 10-game moving averages. So in order to get a 10-game moving average, we have to start with the 11th game because the forecast requires the 10 games before that. So we only have forecasts from the 11th game on. Now I also think there's some non-statistical reasons why this is beneficial. The NBA season starts in mid or late December, and it can take several games for the team to gel and be performing at a level that's representative of their talent. Also, it's the holiday season, so there are a lot of competing activities outside of the game that players must deal with. So, for statistical reasons and for real-life reasons, starting with the 11th game with our forecast, I think, is actually a good idea. Now, as you can see from this graph, the scoring for the Heat is actually all over the place. You know, it can go up and down drastically over the course of the season. So it's not uncommon to have 10 or even 20-point swings from game to game. So this data is very variable. So we'll have to keep that in mind as we figure out our time series forecasting and our errors. Now, I'm not going to go into each one of these in depth because I've done so on the previous couple of videos, but there are 4 possible methods for doing forecasts. We have the naive approach, which just repeats last periods, in this case last games, score. We have the simple moving average, which simply averages together a certain number of games to figure out the forecast for the next game. The weighted moving average is similar to the simple, except we give weights to games that are more recent than further in the past. And then we have the exponential moving average, which, using the smoothing constant, just by changing one number in the formula, we can emphasize games that are more recent, or we can spread the emphasis out over further games into the past. Now this is actually the score forecast for all the forecast models we're going to consider in this problem. This graph is a mess. You can't really read it. There's just too much there. However, what I want to point out is that the actual score, that's in the dark blue, so you can see that jumping up and down quite a bit. And then we have 3 moving averages, a 3-game, a 5-game, and a 10-game simple moving average. We have a 3-game and 5-game and 10-game weighted moving average. And then we have a exponential moving average with an alpha of 0.5, an alpha of 0.3, and an alpha of 0.1. And then we also have the naive approach. We're going to go ahead and include that in this model. So we have numerous models we're going to test to see which one produces the best forecast for games as they progress throughout the season. So let's just remind ourselves what forecast error is. It just compares the forecasted data with the actual data for any given period. So in this case, we're going to be comparing the score from any given game to what we forecasted that game to be from past data. It can help determine the accuracy of different forecasting models. So in this case, we're going to use the naive, the SMA, the WMA, and the EMA, and it helps us determine how good those are over the long run. It uses very simple math, nothing more than adding, subtracting, dividing, and multiplying. And again, our goal is to find the lowest possible error among all these alternatives. The reason I'm using so many models in this problem is so you can really see not only how each model compares to each other, but also different versions of each model. So we're using 3, 5, and 10 game averages. We're using alphas of 0.5, 0.3, and 0.1. So within each model, we're going to have different periods and different alphas. And again, the general formula for the error is just the actual minus the forecasted, and the most obvious way to think about that is the weather forecast I just gave you. Negative error means that we underpredicted, while positive error implies that we overpredicted. Now again, what we're asking ourselves is, how far off are our predictions from the actual data for any given period? And when we graph the actual data alongside the predicted values, how close are they together? I mean, physically on the graph, how close are they together? We're going to use our 3 simple error measurements we did in the last video, and again, I'm not going to explain each one. If you want to learn about these in depth, please watch the previous video. We have the mean absolute deviation, or MAD, which is basically the distance from the actual and the forecast. We have the mean squared error, which is basically the distance from the actual to the forecast squared, and that helps us really separate the two. And then we have the mean absolute percentage error, or the MAPE, and that is simply the percentage that our forecast is off from our actual data. So when we figure all this out, and all the possible combinations, we actually have 30 values to find in this video. Now, of course, am I going to sit here and make you watch me find 30 values? No, it took me several hours to do all this. However, I'm just going to type into this chart as we go the values I came up with. So if you look there on the left, we have the naive model. Then we have 3 simple moving averages, a 3, 5, and 10 game. Then we have a 3, 5, and 10 game weighted moving average. Now what does that n-1 mean there? That means that the weightings are going to be linear. So for example, for the 3 game weighted moving average, I'm going to give the most recent period, or the most recent game, a weighting of 3, the game before that a weighting of 2, and the weighting of the game before that a 1. For the 5 game weighted moving average, it'll be a weighting of 5, weighting of 4, 3, 2, and 1. And for the 10 game, the same thing, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So the n-1 just means that the weightings for the weighted moving average will be linear. Then we have the exponential moving average. We're going to use or try out three different alphas, 0.5, 0.3, and 0.1. Just remember that the alpha of 0.5 will give a great deal of emphasis to more recent games, and remember the alpha of 0.1 will spread out the emphasis greater into the past. So it will evenly incorporate games that go further and further into the past versus all up front to the most recent. Now, before you think that I'm actually making this stuff up, I actually did do all this. So it took, like I said, 2 or 3 hours to get all the data typed in and then put all the formulas into Excel and everything like that. So yes, I did figure out all 30 of these values. I'm not making it up. So let's go ahead and go on from here. All right, so our first one is the naive approach. Remember, naive approach just repeats last period's or last game's actual data. So that's why this looks like sort of 3D funky graph, because the naive approach is literally just the entire score shifted to the right. So our forecast for the next game will just be the score from the most recent game. That's why it looks the way it does. It looks very weird, but you can really see exactly what this is. It's just the shifting of the forecast is one game into the future. So when we do the calculations for the MAD, the MSE, and the MAPE for the naive approach, we get a MAD of 12, an MSE of 231, and a MAPE of 13.34%. So for the MAD, that means the naive model was on average 12 points away from the actual score. That doesn't mean a whole lot right now until we get some other MADs in that column. But just realize that using the naive approach, we were about 12 points off on average from the actual score in our forecasting. And the MAPE shows us that we were about 13.34% off the forecast from the actual score on average. So here are our three simple moving averages. It's a lot of lines, through our graph here, but remember the blue is just the actual score, and the 3, 5, and 10 game are red, green, and purple respectively. Now if you notice that the 3-game SMA jumps up and down a lot like the actual score does, and that should make sense. We're only using 3 games in the past, so it's going to be more responsive to high and low games as they occur. Of course, the 5-game simple moving average is going to be a bit smoother, and it is. If you look at the green line, it doesn't jump up and down nearly as much as the red one does. It's much more calm as it goes throughout the season. Now the 10-game moving average is going to be even flatter because it is incorporating 10 games from the past to make its forecast. So that purple line just it goes right through the season. It doesn't go up or down very much. It just kind of, it goes up and down a little bit as it goes on throughout the season. And even at the end, when they have that terrible game right there at the end, the 10-game simple moving average just ticks down a little bit compared to the 5 and 3 game. So you can really see that the 10-game simple moving average, by incorporating 10 games from the past, does not have as many violent up and downs as the 5, 3, and actually the score. Now, the MAD, the MSE, and the MAPE for those 3 simple moving averages. As you can see, the MAD is 9 for all 3 of those simple moving averages, which is quite a bit less than naive approach. So on average, those simple moving averages were 9 points away from the actual score. As far as the MSE goes, it appears that the 5-game simple moving average had a little bit lower MSE than the other 2. And the same thing goes for the MAPE. So within the simple moving averages, it appears that the 5-game simple moving average was the best model, because we have a MAD that's the same as the other 2, we have an MSE that's the lowest of those simple moving averages, and we have a MAPE that's the lowest of those simple moving averages. Now on to the weighted moving average. So again, the score is in the blue. It jumps up and down quite a bit, and the 3-game weighted moving average follows very close to that score. Again, because it's responsive to the most recent game, because it places a lot of emphasis on that most recent game. Now the 5-game weighted moving average is a little bit smoother, notice it doesn't have as many up and downs as the 3-game does. Like, for example, if you look at around game 41 or 42, you can see that the 3-game WMA jumps up because of that previous game that had a high score, whereas the 5-game WMA doesn't jump up nearly as high. And the same thing is true when they have that low game the next time. The 3-game weighted moving average goes down quite a bit, whereas the 5-game goes down just a little bit less. Now, if you look at the 10-game weighted moving average, that's the purple line. Again, it just kind of meanders through the data because it's using 10 games in the past. However, it is taking into account more recent games. It is weighing those a bit more heavily. So even though it doesn't jump up and down as much, it is somewhat responsive to more recent games. And you can see that again right around game 42 in our series, where we have that big game up and then a big game down. The 10-game weighted moving average doesn't nearly jump up as much as the other two. Now, when we figure out our MAD, MSE, and MAPE for the weighted moving averages, you can see it's relatively comparable to the simple moving average. So we have MADs of 10, 9, and 9. We have MSEs of 147, 133, and 126. So that 126 value for the 10-game weighted moving average is our lowest yet. So right now that's looking pretty promising. Now if we go over to the MAPE for the 10-game weighted moving average, it is also the lowest as of this point at 9.91%. So on average, our forecasted values were 9.91% off of the actual values. So given all of the information we have so far, it really looks like our 10-game weighted moving average is the best model. And finally, we have our exponential moving average. And here we used 3 different smoothing constants, or alphas, 0.5, 0.3, and 0.1. So if you take a look at the EMA of 0.5, that's the red line, it really jumps up and down with the actual score there in the blue. So again, around game 42 or 41, we have a big jump up and then a big jump down. Well, the EMA responds quite readily to that up and then violent down, as you can see there in the red line. Now the EMA of 0.3, remember, it takes into account games further into the past, and it relatively lessens the emphasis on the most recent game and spreads it out further into the past. So we would expect that green line not to react nearly as violently as the red line does to changes game by game. And it doesn't. So even though it does jump up and down a bit, you can see that whenever the red line jumps up, the green line, it jumps up as well, but not nearly as far. And the same thing downward. So whenever the red line goes up, the green line goes up too, but not nearly as much. Now the EMA of 0.1, look at that line, that purple line. It's almost a straight line right through that data. Of course, now why is that? If you remember, the EMA of 0.1 really lessens the emphasis on the most recent game and spreads out the emphasis way into the past. So any individual game, as it comes up, does not impact the EMA of 0.1 hardly at all. So even if we have a sharp up or down, so let's take a look at that game 41, 42 again. We have a huge jump up, and we have a huge fall down, but the EMA of 0.1 barely moves. It blips up, it blips back down just a bit, and goes on its way. So you can see that the EMA of 0.1 is much smoother. It's much more flat because it's spreading the emphasis further into the past. So here is our full chart. We can go ahead and add in our EMAs. Now for the MADs, we have pretty much the same thing we did for the weighted moving average, 10, 9, and 9. And you can see, except for the naive approach, the MADs are either 9 or 10. It's pretty consistent. Now if we look at our MSEs for the EMA, we have 145, 129, and 123. Now a few things to note. Overall, the 123 MSE is the lowest by far. So we have the 123 at the EMA of alpha of 0.1. We have an EMA of 129 and alpha of 0.3. And in our chart here, in our column, those are both pretty low. Only the 10-game weighted moving average and the 5-game simple moving average are lower. So you can begin to see that this EMA model tends to be, better than the other ones. Not by a whole lot, but it tends to be better. Now, if you look at the MAPE for the EMA at an alpha of 0.1 is 9.81. And again, that is the lowest MAPE we have in our model. So remember in my last video I said that sometimes in our chart here, in our table, we're going to have MADs and MSCs and MAPEs that aren't consistent with each other between models. So the MAD it's hard to determine which model is best using the MAD because they're all 9s or 10s. Besides the naive approach, they're all 9s or 10s. Now if we go to the MSC, well, yeah, the EMA at 0.1 is 123, but we do have some low values elsewhere in that column. Now for the MAPE, we have the value of 9.81 for our EMA at alpha equals 0.1, but we also have a low MAPE for the 10-game weighted moving average and the 5-game simple moving average. So we kind of have to use a value judgment here. Which model do we think is the best at representing our forecast versus our actual scores? Well, if we were to pick one, we would have to say that the exponential moving average with a smoothing constant, or alpha, of 0.1 is our best model. It has a low MAD that's similar to others at 9, but it has the lowest MSE at 123, and it has the lowest MAPE at 9.81%. Now I do want to pause here because even though the EMA at 0.1 is the lowest, it's still not that great because we're still, on average, 9 points away. Our forecast is 9 points away from our actual score. Our forecast is on average 9.81% away from our actual score. So even though it's the best out of all these models we tested, it's still not that great. And the reason it's not that great is because the team's scoring is relatively all over the place. It's extremely variable. We just can't nail down a forecast because the Miami Heat can have swings of 10 or 20 points between games. There's only so much we can do with data like that, and this represents sort of that limit. Now this chart is kind of overtime, so if you don't understand what this chart is saying, it's really okay. So this chart is actually a correlation chart, and we are correlating the actual score throughout the season with our forecasted score using our models. Now the most important column here is the first column. And that's where we're correlating the score with each of our models. Now if you know anything about correlations, you know that correlations go from -1 up to +1. A correlation of +1 exactly is an exact correlation. So that's why the intersection of score and score is 1. It's a perfect correlation because it's correlating with itself. Now what we're going to do is go down that score column, disregarding the first one, which is score and score. We're going to look for the highest correlation between score and our models. So if we go down that column all the way to the bottom, you'll notice that the exponential moving average with an alpha of 0.1 has the highest correlation with our actual score. So we're correlating our forecasted values of EMA 0.1 to the actual score. And that has a positive correlation of 0.32. Now if you know anything about statistics, while that's a positive correlation, that is not spectacular. A more impressive correlation would have been around 0.6, 0.7, 0.8. So that just emphasizes my point from the previous slide that even though the EMA with an alpha of 0.1 is our highest, it still isn't that great. But this correlation chart helps us emphasize and support the idea that the exponential moving average with an alpha of 0.1 is our best model. Now likewise, if we find the next two highest correlations, we have the 10-game weighted moving average with a correlation of 0.29 and the 5-game moving average of 0.28. If we go back to our previous slide, we will see that that 10-game weighted moving average had an MSE of 126 and a MAPE of 9.91. And the 5-game simple moving average had an MSE of 128 and a MAPE of 9.95%. And we go back to our correlations. There they are. So we can do these correlations between our actual scores and our forecasted scores just to sort of support our conclusion of which models work the best. So how can we interpret this data? Why did the 10-game average and the exponential moving average of 0.10 turn out to be the most reliable forecast models for the Miami Heat scores? Now remember, this wasn't by much though, but they were still the best. Now here's our answer. The scores had a high game-to-game variability. If you remember the score chart, it's up and down, up and down, up and down, just all over the place. Therefore, the near-weighted models that use short averages like 3 games or an alpha of 0.5 or whatever were affected much more by game-to-game gyrations in the data. So when the Miami Heat went out and scored 15 more points than they did last game, and then the next game they scored 20 less points than that previous game, well, that's really hard. That has a lot of effect on short average models like 3 games and so forth like that, and especially the naive approach. So because the game-to-game data is so variable, the short averages were just too sensitive to that variability. So the longer-term models were able to sort of iron out this variability. And in the case of the EMA, it actually took into account previous games' forecasts. And that's what makes the EMA unique. Not only does it use previous game data, it also used previous games' forecasts. So by taking longer time periods into account, the 10-game moving averages and the EMA of 0.1 was able to iron out that variation. And here's sort of the example I can use. The EMA of 0.1 and that 10-game weighted moving average. So the EMA of 0.1 and the 10-game moving averages is kind of like going down the middle of a road. It's kind of equidistant from the left and the right. There are no extremes. It's kind of the same distance from everything on the right as it kind of is from everything on the left. And if you remember our graph of our EMAs, that purple line sort of went right down the middle of the data. And by doing so, it was able to minimize the error on either side of it. So that's why our EMA of 0.1 turned out to be our best model, because we had a lot of data that fell on either side, but the distance to either side was the smallest. All right, so this is a very complex problem, and I actually bit off a bit more than I could chew when I did all the data analysis for this problem. But again, this is a real-world problem. It's fun. You can actually see how the time series forecasting works on shorter time scales, because this was game to game. And you can see that it works whether it's from year to year, game to game, sometimes hour by hour it could be. If you work at a fast food restaurant, you could figure out time series for customer flow from hour to hour. And, it's kind of, fun. I like to use real world data to show off these ideas. So if you're trying to figure out what the Miami Heat were going to score on their next game, you would not want to look at the past 3 games or the past 5 games even. You really want to take into account the previous 10 games or so. Because even though you're going to be a little bit off, you're going to be off a little bit less. So again, this was just a fun way to look at time series forecasting. I hope you enjoyed it. I'll try to do more examples like this. But again, thank you for watching. I look forward to seeing you again next time.